Hey everyone, welcome to lecture 32. Today's lecture is the very last lecture that has material for which you're responsible for in this course. So today's lecture is the last content that will be covered on midterm 3. I have one final lecture in the course before we launch into the midterm, and then the final 3 class periods are going to be your video project presentations. And you get to vote on the topic of the final lecture on Monday when we return from Thanksgiving break. So today we're talking about compressible flows through a variable area duct. So let me fire up the annotator and we'll get started. Okay. And here we go. So this is section 11.7. We last looked on Monday at section 11.5, and then we skipped over 11.6 and went straight to 11.7. But we're talking about flow through a duct with an area change. So we've talked about this a lot before in this class, but now the flow is compressible, not incompressible. And one of the most intriguing results that we get is that when you have compressible flow, you can actually have flow accelerating through a duct whose area is becoming larger, right? So normally when we think incompressible flows, that can't happen. The area and the speed are inversely proportional to each other. If we have a compressible flow that becomes supersonic with a Mach number greater than 1, that's no longer the case, as we'll see shortly. Okay, so we have compressible flow in a duct, as we've got depicted in the figure here, flowing from section 1 to section 2. And 4 things can affect the flow rate: changes in the area, viscous friction at the wall, adding or removing heat, or shaft work. Here, for the purposes of this course, this lecture, we're assuming the flow is frictionless and adiabatic with no shaft work. So the only thing that can affect the flow rate is changes in cross-sectional area, and of course the pressure that's driving the flow. The continuity equation for this flow is m dot equals rho AV equals a constant, right? We've seen this equation a bunch of times before. Normally for incompressible flow, we would assume that the density was a constant. We don't assume that here. Okay, so in chapter 3, way at the beginning of the course, we applied Newton's second law, F equals ma, to the inviscid flow, steady flow of a fluid particle. And we got the following equation, which I'm recopying here. dP plus 1/2 rho dV squared plus gamma dz equals 0. And we're going to renumber this equation 1186. For gas flows, changes in elevation just don't change the pressure very much because gas flows are the density is so low, so we can neglect the potential energy term and rearrange the equation in the following way. This is 1187. If we now take the natural log of both sides of the continuity equation, 86, then we get natural log of rho plus natural log of A plus natural log of the velocity V is equal to a constant. It's 1188. And then finally, differentiating that form of the equation, we get d rho over rho plus dA over A plus dV over V equals 0, or rearranging this, minus dV over V equals d rho over rho plus dA over A. This is 1189. If we now combine equations 87 and 89 and use it with the expression you see at the top here for d rho, we obtain the following. dp over rho v squared 1 minus v squared over dp d rho equals dA over A, 1190. Since the flow is isentropic, we know that we can write the speed of sound in the flow as partial P, partial rho at constant entropy. And if we combine the above expression for C with the definition of Mach number and equation 90, we have now this expression in terms of the Mach number. And we'll number this equation 91, the same number it's got in the textbook. Finally, we combine 87 and 91 and we get this final form that dV over V equals minus dA over A times 1 over 1 minus the Mach number squared. I'm going to box this because this tells us this very intriguing results that we mentioned at the very beginning of the lecture. So if we look, we see that dV, a change in velocity, and dA, a change in area, have the opposite signs, right? If this term here, 1 over 1 minus the Mach number squared, is positive, right? So if we have a Mach number much less than 1, if we've got subsonic flow, so a Mach number less than 1 or much less than 1, 0.3 or less, which gives us incompressible flow, then this factor here, 1 over 1 minus the Mach number, is positive, and this holds that dV is proportional to minus dA, right? So if we have an increase in area, we have a decrease in velocity and vice versa. But look what happens when we have sonic or supersonic flow. If we have a Mach number greater than 1, then this factor becomes negative, cancels out this negative sign, and then dV and dA have the same sign. And that amazingly means that for supersonic flow, for a Mach number greater than 1, if we have a duct and its area is getting larger and larger, the velocity is increasing as well, right? It's completely counterintuitive to everything that we've learned in this course so far, but true. So if we rewrite this equation that we just derived at the top here, just factoring it out a little bit differently, we see that in general for a converging passage, a converging duct, for subsonic flow, we get an increase in velocity, but for supersonic flow, in this last column, we get a decrease in velocity, right? And you can see similar trends for all of our different variables here. And then for a diverging passage, for subsonic flow, we get decreasing velocity. That's what we're used to. But then for supersonic flow, we get increasing velocity, right? And this all comes from this equation here, and just looking at whether we get a positive or negative sign from this Mach number squared minus 1 factor, and what that does to the relationship between dA and dV. This also implies that sonic flow with a Mach number of exactly 1 can only happen at an area minimum, right? Because what happens when we have a Mach number of 1 here, then we get 1 minus 1, so we've got 0 here. And then we must, if the right-hand side of this expression is 0, then we've got to have 0 on the left-hand side as well, and that means that dA is 0, okay? dA is 0 when the area is not changing, right? So we either have a local minimum or maximum. So we've either got this situation here on the bottom left or on the bottom right, but we know that when the duct is converging, like on the bottom here, that for subsonic flow, the flow is slowing down, and, or pardon me, the flow is accelerating, right? So that tells us that it's actually this bottom left case of an area minimum where our Mach number is equal to 1. So this explains the characteristic shape that we have on rocket engines, right? We've got this characteristic converging, diverging shape, and the reason that it's like this is so that we can accelerate the rocket exhaust to supersonic speeds. As you'll see in a couple of slides, in order to accelerate a flow to supersonic speeds, we need to have a converging, diverging nozzle, and it's because of this equation.